start with questions if anybody has anything from the homework or whatever else. Hopefully not life questions. I don't know if I'm qualified to answer those. That was a joke, guys. I mean, it was also kind of serious. Mr. Gulick's expertise doesn't extend too much outside of the academic realms. What is the meaning of life? I don't know. You're just going to have to figure it out for yourself. You get all the answers that I can't give you as a math teacher, right? Ava.
So I had a question on like when we started talking about implied domain last class.
Yeah.
So I have it on here.
Are we talking about a homework problem?
No, it was from the notes.
Okay. Let's there it worked. That's so shocking. All right.
It was right there.
Okay.
So I was confused. It was C.
Okay.
No, actually A. Sorry.
Sure.
Yeah, right there. So how did you get the 2 root x minus 4 to x minus 4 is greater than or equal to 0?
Right. So if we're worried about a domain, there's 3 things that you guys would reasonably be responsible for that can cause something to become undefined. Those values that make our function undefined would be things that are not inside of our domain. So the 3 operations are division, when you divide by 0, can be undefined. Square roots, when you square root a negative, we get undefined. And logs, if you take the log of a non-positive, it's undefined. So if I look at example A, of those 3 operations, I don't see any division, I don't see any logs, but I do see a square root. So I know that the square root part, the part under the square root, cannot be negative. That's the same thing as saying it must be greater than or equal to 0. That's where I'm at. Is that okay?
Yeah.
You're welcome. Other questions? Bella.
So we haven't learned logs yet.
Nope, and I wouldn't expect you to do anything with logs.
Okay, so
I'm just
disregard it.
I'm just stating it as a fact.
Okay.
Because at some point, some of us will probably have to take an ACT, and you will see logs on that.
Okay, sounds good.
And I'm just trying to slow roll that in, rather than try to oh, look, we didn't do 3 chapters that you should have done from Algebra 2. Let me start with all that right away.
Okay.
We'll just kind of sprinkle things in as we go.
Thank you.
And I know you don't know what a log is,
No idea.
other than now that you can only take a log of a positive number. Right? You can't take the log of 0 or negative, which is enough for now. Okay.
Thank you.
Deal? Okay. All right. So today we're going to continue our tour of Algebra 2-ish review topics. In section 3, this is a quickie section. We're going to be talking about continuity. So continuity is an adjective we use to describe a function. So I say a function is continuous if I can draw that function without having to pick up my pencil. So for example, that would be a continuous function. I can do that with just one whoop whoop of my pencil, as opposed to, say, something like this, where I couldn't draw it without picking up my pencil. Does that feel okay with you guys? Relatively straightforward, right? Or idea, relatively straightforward idea. Now, what we're interested in here is these places where we'd have to pick up our pencil. These are called discontinuities. And we're going to talk about 3 types of them. The first type we'll talk about is the good old vertical asymptote. Did you guys get a chance to talk about asymptotes last year?
Yep.
I know that you didn't get through a lot. I'm just asking, and it's okay to say no, and it's okay to say yes if it's like some of us came from the regular class or some of us came from an honors class or whatever, so some of us have seen some different things than others, and that's okay. So an asymptote is a line the graph approaches but never crosses. So a vertical asymptote is a vertical line. So something that looks like this would be a vertical asymptote. We also refer to these as infinite discontinuities. Those two phrases could be used interchangeably. So the types of functions that have vertical asymptotes, your most common 2 types that you would have seen in a normal year in Algebra 2 would be the rational function and a logarithmic function. Now, I know that we don't know anything about logarithmic functions, and that's okay. But now we know 2 things, right? That you can't take the log of a non-positive, and the graph of a logarithmic function has a vertical asymptote. 2 things we know about them now. We don't know what any of that really means yet, but we're just like slowly kind of building things in. I'm just kind of sprinkling it in here and there. Everybody's still doing okay? When I say a rational function, do we know what that is? The word rational kind of looks like ratio. What is a ratio in math? A fraction. So a rational function is a fraction of 2 polynomial functions. So for example, something like y equals 1 over x plus 2, or something like this would be a rational function. Everybody's okay with that notion? Smooth move. I'm just joking, guys. So there is a relationship between the denominator of a rational function and the vertical asymptote. That relationship is if I take the reduced rational function and I set the denominator equal to 0, that will give me the locations of my vertical asymptotes. So in this case, my vertical asymptote would be at x equals -2. No big deal, right? Now again, we don't Probably didn't cover rational functions in any kind of depth last year. Is that a fair assumption? Okay. But now we know something about them, right? They have vertical asymptotes. And the way to find the vertical asymptote, or totes, there could be more than one, would just be setting the reduced fractions denominator equal to 0 and solve. What does that usually entail? Oftentimes it'll be factoring a quadratic, which I know you spent a lot of time doing last year, right? Yes. Okay. And we'll look at some more examples here in a second after we burn through these other two types. The next type we'll talk about is called a removable discontinuity. So let's take a look at this. See the little open circle on my graph? That's one point that's missing. That is my removable discontinuity. It's just like a point that's missing from my graph. In your Algebra 2 class, if you had talked about rational functions, that's something you might have talked about. So rational functions are the only thing you could have seen up to this point that would contain a removable discontinuity. And the way a removable discontinuity occurs is if you have a rational function that you can reduce, and in doing so, you reduce one of the factors from the denominator. So to reduce a rational function, you'd want to factor the numerator and denominator. Now, looking at this function, it's clear that the denominator can't factor anymore, right? That's just a linear term with leading coefficient 1. There's a fancy word for those. They're called monic polynomials. Not important, but if you're a names person, show off for your friends. That's what that's called. Now the numerator is quadratic, right? It's a degree 2 polynomial. This most likely can factor. Do you remember how to factor something that looks like this? Since the leading coefficient of that polynomial is 1, right, it's a 1x squared. To factor this, we know we can use the shortcut to factor it. So it's going to factor to be like x plus or minus something times x plus or minus something. Everybody kind of remember that? To figure out those somethings, we want to find the two numbers that multiply to give us -2 and add to give us -1. What are two numbers that multiply to give us -2 and also add to give us -1? -2 and +1. So I'm going to have an x minus 2 and an x plus 1. Does that feel okay? Look like something you did last year? You're like, finally! Now, if I look at this fraction, do you notice anything in common between the numerator and denominator? They both contain the factor x minus 2, right? So we can reduce those out. Which is going to equal x plus 1. However, what I've written here is not completely correct. Mr. Kulik, why not? Well, if I plug x equals 2 into this function here at the very start, I get 0 over 0, right? If this is equal, if I plug x equals 2 into this, I should get the same thing, but I get 3. Oh, no. Yes, sir.
We need to set that x plus 1 equals 0, and then it'll be like the minus 1.
Nope. So what all I'm doing right now is demonstrating that we wrote that this is equal to this, right? We've strung them together a bunch of equal signs, so those two things need to be equal. If that's the case, then any number I plug in for x should give me the same value either place, right? You guys agree with that? But they don't, because I've just shown you when I plug 2 in to the first thing, I get 0 over 0, and I plug 2 into the last thing, I get 3. You guys see that? Now, if I had picked any other value for x, this would have been fine. So what am I going to do to fix this? Well, just not going to allow x to be 2. If I pick any other value for x, this is true. Now, the question you should be dying to ask is, Mr. Kulik, how in the blazes did you know that 2 was going to be the problem? Right? That should be the natural question. And my answer to you is the thing from the denominator, the factor from the denominator that got completely reduced. If I set that equal to 0 and solve, that gives me my value here. And those will be the removable discontinuities. So all we're saying, we have a rational function. If we can factor it and reduce, and we reduce a factor from the denominator completely so that there's no more copies of that left in the denominator, that will create a removable discontinuity. To find the location of that removable discontinuity, we take the reduced factor, set it equal to 0, and solve. Is that okay? And the reason that's important is, without stating those removable discontinuities, the two things that we're saying are equal aren't always equal. There'll be some spots where they're not. And we have to make sure that we account for that. Is that okay? Great. The last kind is called a jump discontinuity. And what a jump discontinuity looks like, this is something you would not have seen in your class last year. Oh, yay, Mr. Kulik. You don't feel underprepared now. You shouldn't feel underprepared now. I've been trying to be very clear and helpful in reviewing these things and not just bulldozing past. Have we felt okay so far? I know it was kind of a lot of information thrown at you there, but I tried to go slow through it, right? Be really clear as to what we're doing. What we're looking at here is a graph with a jump discontinuity. You see how one part of the graph is here, and then it jumps to and starts going from a new location somewhere else. You guys see that? Notice one end of the graph has an open circle and one has a closed circle. Why is that the case? What would happen if they were both closed? What would that mean if they were both closed? Wouldn't be a function. Why not? If both of those circles were closed, it would not be a function. Why not? That graph would fail the vertical line test. Because at x equals 0, there'd be two places where the graph would intersect that vertical line. Does that feel okay? We can see that? Just call back to a previous topic, right? That was something we looked at in section 1. Okay. So, Mr. Kulik, you just threw a whole bunch of gobbledygook at me, right? What am I actually going to be responsible for being able to do for you? Fair question. Here's what I would tell you. I would expect you to be able to look at the picture of the graph that I've given you and tell me the location of the discontinuity and the type of discontinuity from a picture. I don't need you to do anything algebraically. I did those examples because I know that we're short on some of those skills and I wanted to just kind of touch on them here and there when I can. But basically that's all I need from you guys for this section is be able to look at the picture and go, okay, this one's a jump discontinuity at x equals 0. That would be enough. Cheyenne.
Do you solve the jump one the same way you do the second one?
We're not going to talk about algebraically how you would do the jump one. That's beyond the scope of what I would expect you to even seen in a previous course. But what it basically boils down to is you'd have something called a piecewise function. So in a piecewise function, it defines the function in pieces. So it's saying when x is less than 0, I should use a different color. This part of the graph, this is how we describe it. It's the function is x minus 1. So I would plot to get that part. And when the function is greater than 0, so this part of the graph, I use this part, or this function. So x plus 1. That's what it would look like, though, is you'd have some piecewise function. There's nothing else that you could have possibly seen in a high school classroom that would give you a jump discontinuity aside from some kind of piecewise function. Okay? And I think depending on how your teacher described an absolute value, they could have used a piecewise function to define an absolute value function, but that would have been the only time you would have maybe seen a piecewise in a high school classroom before this point. That's it for 1.3. I just want you to be able to look at a picture, tell me the type of discontinuity, and where it's happening at. That's all I would ask from you. Yes, Ava.
So for the vertical asymptote discontinuity,
Mhm.
will we get that equation to figure out where it is? So we're given the y equals 1 over x to figure out where the discontinuity is given.
No, I think that what you'd end up with is like a picture like this. Okay, so this might be what you'd get. Let me do that to clean things up a little bit. So I see vertical asymptote here, right? And I see a vertical asymptote happening here. So I'd write vertical asymptotes at x equals -3 and x equals 1. I'm just reading it from the picture. I would not expect you to do any kind of algebraic manipulation, particularly since I know that that was not a topic you guys did a lot of last year. And by a lot of, I mean any. But I feel like we can do that, right? Look at the picture and tell which type it is and say, like, okay, that's where it's at.
Yeah, I just didn't know if we like could see it by just looking at it.
Yeah, no, just picture should be good, right? Everybody feels like I can do that. My eyes were good. All right. Next up, we're going to talk about section 1.4, which is about intervals of increasing, decreasing, and constant. And then also extrema. Ah! So I'm going to define all of this stuff with like a couple of pictures, okay? So let's say we have some function that looks like this. Let's pretend we have a little person that's walking along our function from left to right. The sections in which that little person is walking uphill are the sections where the function is increasing. So that section there, we're increasing. The section where your little person is walking on a flat section, that's where the function is constant. And the part of the function where that little person is walking downhill, that's where the function is decreasing. Everybody feel okay about what we mean by increasing, decreasing, and constant? All I'd ever ask you to do is be able to look at a picture and pull the values from the picture. Okay with that? All right. Let's do a example. Okay, let's say we want to find our intervals of increasing, decreasing, and constant. and we're given this picture. Looking at this picture, how many intervals do we see that the graph is increasing? How many parts of the graph where it's increasing? You should see 2. You should see right at the beginning, and then again here at the end. Everybody agree with that? Okay. So if I look at the beginning, this left-hand arrow is like the point -infinity, -infinity, because it's pointing left and down. Everybody agree with that? And the graph stops being increasing at the point -2, 5. You guys agree with that? To write my interval increasing, I'm just going to take the x-coordinate where it starts increasing and the x-coordinate where it stops increasing. And I'm going to write that interval. Because there's more than one interval, I'm going to connect it with the U symbol. And then I'm going to look at the next interval. Notice that the right-hand arrow is pointing up. So that's kind of like the point +infinity, kind of +infinity. And just like I did before, I'm going to start with the x at the start of my interval increasing and the x at the end of my interval increasing. And I'll write those. So forth to +infinity. Note, everywhere on these intervals, I used a parenthesis. Did you guys see that? For increasing, decreasing, constant, always we will use parentheses. So there's never going to be a case where we use a bracket for our interval when we're doing increasing, decreasing, and constant. Everybody cool? Okay. How many intervals do we see that are decreasing? 1. Where is it going from?
-2, 5 to 1.
Excellent. So we have one interval there. So the x-coordinate where it starts decreasing is at -2, and where it stops decreasing, it's at 1. And then, well, there's only one spot left. That's the constant spot that begins at 1 and ends at 4. What do you guys think on this? Pretty easy, right? You're just using the picture and reading the stuff from the picture. Notice, did I ever use the y-coordinates at any point when I did these intervals? No, all x-coordinates. Everybody's cool? Okay. That's about the gist of that topic. Let's talk about extrema. There's 2 types of extrema. There's maxima and there's minima. Notice that maxima is just the plural for the word maximum, and minima is the plural for the word minimum. There's actually 2 types of maxes and mins. There are local maxes and mins, and then there's global or absolute. Depending on who your teacher was, they may have used one term or the other. They are interchangeable. There's not a right one or a wrong one. I end up saying global more often than not because that was my first introduction to the term, and that's what stuck. But if you like absolute, that's fine. So let me just kind of explain this with a picture. So let's say we have a function that looks like this. When we talk about the maxima, we're talking about any relative high point on our graph. So if I look at my graph, I see how many maxima? I should see 2. I should see one right here and one right here. Everybody agree with that? The overall highest point is the global maximum. And then any relative local high point is a local maximum. So if I just take the neighborhood around that, it's the highest point in its neighborhood, but it's not the highest point overall. Okay? How many minima do I see? Just one. It's this point right here. Is this point local or global? It is local. Why is it local? Because the ends of the graph are pointing down, so there's certainly points on this function that are lower than that minimum in the middle. It is just a local minimum. So what can I say about a function that has arrows at both ends of its graph? It can't have both local, or it can't have both global minimums and global maximums, right? It can't have both. Here's a question for you, though. Can I have more than one global maximum or global minimum? You could. Let's look at a picture of how that could happen. What if I had something that looked like this? Both of these would be global maxes because they have the exact same height. They are equal, tied for first as the highest point. They would both be global maximum. So that's how you could have more than one, is you just have a bunch of ties for first. Does that feel okay? So if we're looking at a graph, this is relatively easy to do, right? You just find the point and then read the x and y coordinate from the graph. Yes? Oh yeah, absolutely. No, that's needs to be taken care of. All right. What if instead, though, of giving you a picture, what if I asked you to do this? So what if I ask you to find all of our extrema and then write our intervals of increasing and decreasing? And all I've given you is an equation.
Can you plug it in your calculator?
Yeah, we would definitely start by typing that into our calculator. So I'm going to press the y equals button up here at the top left, and then just type in the equation as it appears on my calculator. So notice that button above the division sign is how I get an exponent. And then I just use the right arrow to move my cursor out of the exponent once I've typed it. God bless you.
Thank you.
You're welcome.
And then press back to trace, and then or out first. That'd be helpful.
Yeah, I'm going to do zoom standard because I don't remember the window I last used. I've used the calculator like 2 times already today and probably have gone ahead and moved my window around all over the place. So if I look at my picture here, I have a global minimum here at this point. I have a local maximum up here at this point, and a local minimum down here at this point. Everybody kind of agree with what we're seeing there? Now, what I want to do, though, is I want to find the actual coordinates for these. The easiest way to do that is to use your calculator. So if you press the second and trace button, as Bella had said, you can notice that there is a command called minimum and a command called maximum. We're going to use those. So I'm going to start by finding that global minimum that was on the left first. To do that, I'm going to select the minimum command. Now the calculator, if you look at the bottom of your screen, is going to ask us a series of questions. It's going to ask us for a left bound, a right bound, and a guess. So the left bound just wants me to move my cursor, which I can see flashing right there, to the left of where I think that global minimum is at. So to move my cursor, I'm just going to use the left and right arrows. Just going to move that guy, and it looks definitely left of where the minimum is. I'll press enter. Now it asks for a right bound. So I'm going to go ahead and move my cursor over there. I see it. That's definitely on the right side of that minimum. I'll press enter again. And then it asks for a guess. Here's the thing with the guess. As long as there's only one of the kind of extreme point you're looking for in between your bounds, your guess doesn't matter. So you could waste your time and move your cursor close to where you think that minimum is, or you can just press enter. If you give the calculator a good guess, it'll find that answer faster, but it's going to find that answer so fast that you won't be able to tell that it was faster anyways. Like it's going to be microseconds faster, so you won't even notice that it was any faster. So we have a global minimum at this point. So let's say we're going to round that to 3 decimal places maybe. I missed whatever that third one was. I don't remember. Oh, 2, 4, 3, and then 6, 5, 3. So that's our global minimum. And I also noticed that my graph is decreasing from negative infinity down to that global minimum, right? So I might as well write that in as well. Now let's find this local maximum next. So second, trace, pick the maximum command, then I move my cursor so that it's on the left side of that maximum. That spot looks pretty good. I'll press enter. The right bound now is going to move my cursor to the right side of that local maximum. That looks good. I'll press enter, and then the guess doesn't matter. And I have negative 0.316, and then 1.495. And then if I look at my picture, I notice from that global minimum to the local maximum, my graph was increasing. So I'll go ahead and write that part of my interval. Then I'm going to find this local minimum next. So again, press second, the trace button. I'm going to select the minimum command. The calculator is going to first ask me for a left bound, so I'll just move my cursor somewhere to the left of that minimum, press enter. Then for the right bound, I'll move that cursor somewhere to the right of that minimum, press enter. And then the guess doesn't matter. So 1.059 and then negative 3.030. I think that's right. Oh, 030. Okay, and then I just need to complete the rest of my intervals. So I notice from the local max to the local min, our graph is decreasing again. So I'll do that from local max to local min. And then I noticed from the local min to positive infinity, the graph is increasing again. And there I go. Do we feel okay with what I did there? Just using my calculator to do that stuffs. If you get to the homework and you feel like you can't remember how to use the calculator to do that, what can you do? Go back to the video and find at minute whatever it is now, something or something, 55 minutes in or so, or 50 minutes in or so, you can watch the buttons again. You know what I mean? Which is nice, right? That's it for section 1.4. Mr. Kulik, we're cranking today, huh? Well, you know, it's nice because a lot of these concepts are very visual. They're a little light on the computation side, which usually makes them a little bit easier to process. All right. The next thing we're going to talk about is symmetry. Symmetry is another adjective we can use to describe a function. So there's 3 types of symmetry that we're going to talk about. The first is symmetric with respect to the x-axis. So I'm going to use the abbreviation WRT for the phrase with respect to. That's a fairly common math phrase, so I'm going to use that abbreviation because it's going to pop up a bunch of times here in this lesson. And it saves me a lot of letters. That makes me a good mathematician by being efficient, not lazy. That was supposed to be a joke. You could have chuckled a little bit, or at least smiled at it, like you understood what I was talking about, but I get it. It's after lunch, and the lights are off, so I get it. All right, what is it going to look like when I have a graph, or the graph of a function that's symmetric to the x-axis? It'll look something like this, where I notice that if I took the part that's below the x-axis and reflected it across the x-axis, it would be exactly the same as the other part of the graph. Is that okay? So if I take this point here, this would be the point A comma f of A. This point down here would be the point A comma negative f of A. You guys agree with that? What that's implying then is that f of x should equal negative f of x. That's like our algebraic interpretation. So what's that? What is that really saying? This always confuses students. So if this was negative 3 down here and this is positive 3, right? If I take positive 3 and I make it negative, that's a point. Or if I take negative 3 and make it negative, it'd be positive 3. That's a point, right? That's what it's saying. It's okay? Okay. What's the next type of symmetry do you suppose we're going to talk about? This is your teacher instinct now. Symmetry with respect to the y-axis. Yeah, of course, right? Because why would you do the x-axis and not then immediately do the y-axis? So again, here we should see the same thing, correct? If you take the part of the graph that's on the left-hand side of the x or the y-axis, and we reflect it across the y-axis, it should give you exactly the part that's on the right-hand side of the y-axis. So if this is the point A comma f of A, this would need to be the point negative A comma f of A. So what that's saying is that f of negative A is equal to f of A. We have a special name for functions that have symmetry with respect to the y-axis. They're called even functions. Is everybody okay so far? Okay. The third kind, we've done reflection across the x-axis. We've done a reflection across the y-axis. What do you think the third kind is going to be? Well, come on, guys. It's going to be 180-degree point symmetry with respect to the origin. I said that condescendingly, like you would have come up with that. But after I show it to you, you're going to be like, oh, that's a terrible name to give this thing, even though it's like very descriptive. Let's do that first. Okay. So what is this type of symmetry going to look like? So if I take this part of my graph that's on the left side of the origin, and I first reflect it across the x-axis, and then reflect it again across the y-axis, it should give me exactly the part of the graph that was on the right side of the origin. So what is this 180-degree point symmetry with respect to the origin really? Both a reflection across the x and then a reflection across the y. Or you could have done it in the reverse order. You could go across the y and then across the x. You'll get the same result. Oh! Yeah, I guess I should have come up with that. There's one or the other or both would be the third type of symmetry. Oh, Mr. Kulak. Ha 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 ha. That is a terrible name they give it. Well, the idea here is like, if I say I take this point and I like tie a rope to it, to the origin, and then I spin it around 180 degrees, oh boy, it's gonna like give me this point down here, right? That's what it's saying, like 180-degree point symmetry is if you grab each point and like you tie a rope to it and a tie rope to the origin and you'll loop it 180 degrees, you're going to land on the function again. That's why they call it 180-degree point symmetry with respect to the origin. But like, goodness gracious, Mr. Gullit, couldn't they just said X and Y symmetry? I don't know. That's just the name they call them. Does that make sense to you guys, though, what I'm drawing there? All right. So if this is the point A comma f of A, this point down here would have to be the point negative A comma negative f of A. So we should say that negative f of A should equal f of negative A should equal negative f of A. And this kind of symmetry gets a special name. These kind of, or functions with this kind of symmetry are called odd functions. Everybody doing okay? Pace is okay? I'm not going too fast through any of these? Trying to make sure I give you guys some time to process while we're going. Let's do some examples now, because this is not a topic that you probably talk about in your Algebra 2 class. Even I don't think the honor students really have seen this topic before, so. So for each of these functions we're going to decide whether they are odd, even, or neither, and then we're going to prove it algebraically. I know, settle down, I used the P word. This is math class, that's going to happen from time to time. Don't have any geometry trauma-related nightmares. Okay? So the first thing I'd want to do is to take a look at the picture and decide whether I think this thing is odd, even, or neither. Everybody okay? So I just went to the y equals and I typed it in and pressed graph. If I look at this picture, odd, even, or neither? This is even, right? Where it looks like we're symmetric about the y-axis. So even. Great. If I go back and look to show something's even, I need to show that f of negative a is equal to f of a. Okay? Fair enough. So I'll just say for my proof, I want to show, I'm going to abbreviate that phrase as WTS for want to show. That's what I need to do to finish my proof. So this is what I need to show. If I can show that, then I'm done. When I want to prove something algebraically, the most common practice is to just start with the left-hand side and try to end with the right-hand side. So here I have a function f of x. If I wanted to do f of 2, what does that mean? If I wanted to do like f of 2, what would I do? Just plug 2 in for x and evaluate, right? Everybody agree with that? If I wanted to do f of 7, what would I do? Plug 7 in. If I wanted to do f of negative 5/3, plug negative 5/3 in and evaluate, right? If I want to do f of negative a, what am I going to do? Plug negative a in and evaluate. Is everybody okay with what I just did there? Now I need to simplify negative a to the 4th. What does negative a to the 4th really mean? What does something to the 4th power mean? That's shorthand for repeated multiplication, right? So negative a to the 4th is the same thing as saying negative a times negative a times negative a times negative a. How many negatives are we multiplying together? 4. If I multiply 4 negatives, what kind of number do I get? A positive. And if I multiply a together 4 times, I should get a to the 4th. And then the plus 1 still comes along for the ride. Everybody's okay with that? Now, if I look at this and I look at this, what do you notice? What's the only difference? I've plugged in a in for x. Isn't that the same thing as just saying f of a? So look at what I've done. I've shown that f of negative a is equal to f of a. Was that what we wanted? So guess what? Our proof is over. Woo! Was that better than you thought it was going to be? When we started doing proof? How many of you got like goosebumps when I said that word? Everybody's so scared of this, of the proofs. It's not so bad, guys. Not so bad at all. Okay. All right, let's do another. So I have some g of x equals to 2 times x to the 3rd plus 3x. Let's type that into our calculator and take a look. See if we can figure out what type of symmetry it has, if it does have any symmetry. Notice one of the options was neither, so it's certainly possible that things don't have to have any symmetry. But looking at this, what do we see? Odd, right? You guys agree? Okay. So, to show something is odd, we want to show that f of negative a equals negative f of a. Again, I just pulled that from our definitions that we had earlier, right? You see it? Okay. So just like before, I'm going to start with negative f of a. So when I plug negative a in for x, I get 2 times negative a cubed plus 3 times negative a. Everybody feel good with what we just did? Okay. If I take negative a to the third, that means I have negative a times negative a times negative a. How many negatives? Multiply 3 negatives, I get a negative. And if I multiply a together 3 times, I get a to the third. So I'm going to have negative 2 times a to the third. Everybody feel good there? If I have 3 times negative a, what do I get when I simplify that? Negative 3a. So I'm just going to write minus 3a. Everybody okay there? Now, I notice that if I look at this and what I've got, or what I started with, the g of x, in the g of x, both of my terms are positive. Down here, both of my terms are negative. So if I factor out a negative sign, we have this. And this piece now is exactly my g of x, except instead of x's, I have a's. So this is now negative g of a. And was that what I was looking for? It was. Luke, what's up?
How do you determine whether a graph is odd, even, or neither?
From the picture? I'm basically looking for the symmetry that I saw. So like when I see that, where's my thingy? Like if I reflect this across the x, and then again across the y, it should be the same as the other arm of the graph. Or even if I reflect just across the y-axis, should be identical to the other side. That's all I'm looking at. Is that cool? So I'm just using my eyes. Just using my eyeballs. All right. One more example. Now, your student instinct tells you, what do you suspect this one is going to be?
Neither.
Neither, yeah. Whether you want to pronounce it neither or neither, I don't care. But yeah, it'd be the third option, right? Why would your teacher say this could be one of 3 things, then do 3 examples and not have all 3 things happen as your example? Like, that's just bad teachering right there. Yes, I used the word teachering. I don't think it's a word. All right, so we'll start the same way. We'll go, okay, let's type this thing in. I'm going to expect to see a neither. Well, that's pretty disappointing. That's not a very good picture, is it? What do you guys want to do? Let's fix our window so we get a better look, right? Okay. Which way do I need to move my viewing window so that I can see this thing? Up, right? If we could see further up, that's probably what we need to see because we can just see like the little bottom of the graph right here. You guys agree? So which are we moving then, the X or the Y? Which one goes up and down? Y's. And should be moving the Y minimum value or the Y maximum value? So currently the bottom of my viewing window is at -10 and the top of my window is at +10. What do I need to change? The max, and let's just make that, I don't know, 30 or something. Okay. What do you think? We were expecting to see neither, right? Does this look neither to you? It should. But Mr. Kulik, it's a parabola. Why isn't it even? Well, if you look, there's more parabola on the right side than there is on the left side of the y-axis. That's why it's not even. You have to have an equal amount of parabola on both sides to be even. You guys see that? And it's close, right? It was close, but it's not, close isn't good enough. We're not playing horseshoes, and we're not playing hand grenades. This is an old saying that my father used to say. Close only counts in horseshoes and hand grenades. I don't understand. But this should be neither. So for our proof then, what do we need to show? Well, we need to show that it's not even and that it's not odd. Everybody cool with that plan? Now, if I look at both of those statements, notice that they both start f of -a. So I can really kind of do this all in one line, just like we've done before. So we'll start with -f of a, and like we've discussed in the previous ones, all that means is we're plugging -a in for x. Now we'll simplify. -a squared is equal to +a squared, right? So we'll have 4a squared. -3 times -a is +3a. And then the 9 just stays the 9. Now if I look at this, and I compare it to h of x, are those identical except for the variables? No. What's different? Yeah. That is different, right? So this is not going to equal h of a. They are different. There's a sign that is different. Everybody see that? Okay, so we've taken care of the not even part. Now let's factor a negative sign off and see if we can see if it's going to give us something that's odd. Everybody's okay with what I did there? If I take this and compare it up here, is that identical except for the name of the variable? No again, right? This time the 4a squared is negative and the 9 is negative, which they're not supposed to be. So what can I say? Then this is not negative h of a. So I've done that part, and I'm done. How do you guys feel with what we've done today? We did a whole bunch of stuff, so be proud of yourself. At this point, you guys should be able to do then up to problems number 22. So we should be able to do up to 22. I think that I assigned to 12 already, right? That was last time was through 12. Let me go look here. Yeah, so 13 to 22 is what we're tacking on now. Remember that last assignment I don't think was due this week, or was due Sunday's problem set, right? That was part of this coming
Wait, so it
Sundays.
was 1 through 4 was due today, and then 5 through 12 was due next.
So this 1 through 4 was due last time. This Sunday, we've assigned 5 through 12, and I'm about to edit that now to be 13 to 22. And then I'll save that. So as I assign new stuff, I'm just going to update the problem sets on my Notre Dame. Cool with that? And let's see, we meet today and then Wednesday and then Thursday also. I think Thursday's the X day. So anything that we did Thursday would not appear on the problem set. But I would say, guys, Thursday might be a good day to make sure that you've done up through 22 in the problem set, because we might be having our first homework quiz at some point this week. That short schedule seems like maybe a good day to do that. So just giving you a heads up, you guys are free to go.
How do your homework quizzes work? So do